Welcome back, everybody, to the second part of graphing stuff that's over x, otherwise known as rational functions. So rational functions, in essence, are fractions. And they're important because they're important to look at separately because we're talking about fractions where we have x's in the denominator. We saw this in the previous video where we looked at the reciprocal function, but now we're going to beef it up a little bit more. In this course of study, in this video, we are going to look purely at rational functions that are a linear function over a linear function. We can go beyond that to any polynomial on top, any degree polynomial on top, any degree polynomial on the bottom, but we're going to keep it simple for now. We'll dive into that other stuff later if you want to. For those of you studying math standard level, this is as far as you need to go. You only need to worry about the linear style rational functions. So let's get into it and talk about the important parts of these functions. So if we have f of x, when will it equal 0? If I put equals 0 up here, when will that happen? Well, that's going to happen when the numerator is 0. Think about it. It's a fraction. When can fractions equal 0? That's when the top is equal to 0. Okay, so when is f of x undefined? F of x is undefined when the denominator is 0. If we divide by 0, the world ends, and we don't want that to happen, so we're going to say it's against the rules. And what does that mean? Well, that means that we have a vertical asymptote at that value, or values of x as we get to the more involved problems. What about, let's ask this question, what about y-intercept? Well, we get y-intercept by letting x equal 0. That's the same for any function. Great, cool. But since this is an offshoot of the reciprocal function, that means that there's a horizontal asymptote too. For the 1 over x graph, it was y equals 0, but how do we find this now? Well, we're going to use what's called a limit. We're going to take the limit of f of x as x gets really big. We're going to look at what happens. And it should be getting closer and closer and closer to something. So let's start by looking at what's the limit as x gets really huge of 1 over x. Well, as x gets huge there, we're taking 1 over bigger and bigger and bigger numbers, so this is effectively becoming 0. As x gets bigger and bigger and bigger, 1 over x gets closer and closer and closer to 0, so we say its limit is equal to 0. And, oh, that was the horizontal asymptote. So let's go to an example and use this stuff. So here we are. Y equals x plus 1 over 2x minus 4. We'll deal with the horizontal asymptote last. But what about the vertical asymptote? Well, that's going to be where the denominator is equal to 0. So we add 4. X equals 2. Good news. X-intercept. That's where the numerator equals 0. So x equals -1 is my x-intercept. Sweet. What was another good feature? Oh, y-intercept. Y-intercept is when we plug in x equals 0. So y equals 0 plus 1 over 2 times 0 minus 4. The y-intercept is -1/4, so it's right about there. Now, we need to find the horizontal asymptote. So let's do this. we're going to take the limit as x gets huge, as x approaches infinity, we say, of x plus 1 over 2x minus 4. Now, if I just look at what happens to this as x gets huge, we're going to get a really big number plus 1 divided by a really big number minus 4. So we have a really big number divided by a really big number, and we don't know anything. So here's what we're going to do. Here's the process that we're going to go through. We're going to divide every term here by x. Why x, you might ask? Well, we're using x because that is the highest powered variable in this rational function. And you're like, okay, great, but why? Why do I care? So we're taking the limit now, and I'm going to simplify, and we'll see why we care. So this first thing becomes 1 plus 1 over x over 2 minus 4 over x. Now let's look at what happens as x becomes huge. Well, what happens as x becomes huge to the number 1? Well, the number 1 doesn't care whether or not x becomes huge, gets small, or completely disappears. It's still 1. What about 1 over x? What happens to that as x gets huge? Well, we talked a second ago that that gets closer and closer and closer to 0. So its limit is 0. On the denominator, what happens to 2 as x gets huge? You're thinking, 2's like the honey badger. 2 don't care. We got 2 on the bottom. And then what happens to 4 over x? Well, if 1 over x is getting closer and closer to 0, well, 4 over a really huge number is also getting really, really close to 0. So its limit is 0, and now I just have nice numbers, and this limit is 1/2, and that is my horizontal asymptote. So here's 1. We're going to cut in a horizontal asymptote here, and now we're ready to draw our curve. There's one branch of the hyperbola, and the other branch will always be diagonally across from it through these asymptotes. And there we go. There's our hyperbola. There's the graph of this rational function. I should label my asymptotes. Y equals 1/2, x equals 2, negative 1 comma 0, 0 comma negative 1/4. Label the important points, and we're done. Huzzah! Next example. Oh, but wait, you say, this isn't the same. Well, it's actually easier, and that's the beautiful thing. This one we can look at in terms of the translations. We have gone right 3 and up 2. Sweet. Right 3, 1, 2, 3. How do we find the y-intercept? The y-intercept is when x equals 0. Okay, so this is going to be y equals 1 over negative 3 plus 2. So 1 and 2/3. And then the x-intercept, well, the x-intercept is, well, this one's a little bit trickier, but it's when y is 0. We can solve this. Negative 2 equals 1 over x minus 3. So cross multiply. Negative 2x plus 6 equals 1. So we'll add our 6, subtract our 6. Negative 2x equals negative 5. X is 2.5. There's our point right there. We can draw our graph in. We have our two curves of our hyperbola, and there we go. We should, of course, label our asymptotes. Y equals 2, x equals 3. And you might be thinking, well, how is this the same as the last example? They look nothing alike other than the graph. Well, ladies and gents, we can make them look the same by getting a common denominator, which would be x minus 3 for this problem. And now the numerator is 1 plus 2x minus 6. The denominator is x minus 3. Combining like terms, we get y equals negative 5 plus 2x over x minus 3. And we could use the skills that we saw in the previous example to find the x-intercept and to find the horizontal and vertical asymptotes, and we will get the exact same features of the graph that we saw using the transformations and finding our intercepts algebraically. And that is where I leave you. I hope you truly enjoy all that is rational functions.